Hi, welcome to a short lecture on physics. My name is Ansh and I'm currently a master's student studying physics at the University of Cambridge. I'm going to be giving you an introduction to simple harmonic oscillators, firstly by looking at a couple of examples, and then by delving a little bit deeper into the mathematical details. So, sound waves, light waves, pendulums, bridges, radios, televisions, and earthquakes are just some of many examples of the importance of oscillations in nature. Oscillations occur when something is displaced, and that displacement results in a restoring force that opposes the displacement. Simple harmonic motion is the simplest example of such behaviour, and it's of huge importance across all of physics. So the typical example of an oscillator is a mass m attached to a spring. So if we have a mass m attached to a spring, we can draw that as follows. So here's just a rigid wall which has a spring attached to it, and also a mass m is attached to the spring. Now we can label this a little bit, so let's label this point as x equals 0 and say that x increases in this direction. Now we'll also label on the acceleration. So the acceleration we'll also take to be in this direction. And then let's label on the spring constant, k. So the key property of springs is that they produce a force F that is proportional, so let's write the proportionality symbol, proportional to the displacement x from their natural length. Okay, so writing that as an equation, we can write F equals minus kx, where k is the spring constant, and this depends on the strength of the spring, or we can say it depends on the stiffness. Okay, so a higher stiffness or strength of the spring would give a higher value for the spring constant k. And the minus sign, so you'll notice there's a minus sign in this equation, this indicates that the force acts in the opposite direction to the displacement. Okay, so if you stretch a spring in this direction, then the restoring force of the spring will act in the opposite direction to try and get the spring back to where its original position was. So now if we apply Newton's second law, so I'm going to write that as apply N2. Then we have F equals ma, which equals minus kx. Okay, so the mass times acceleration equals minus the spring constant times the displacement. So we can alternatively write this using derivatives. If you've done a little bit of differentiation, you know that the acceleration a can be written as the second time derivative of the displacement x. So we can write this as d2x by dt squared equals minus k over m times x, having done a little bit of rearrangement to take the m over to this side. Okay, and now we can write it all on one side and let it equal to 0. And for reasons that will become clear later on, we're going to write this k over m instead as an omega squared term. So we have d2x by dt squared plus omega squared x equals 0, where we have defined omega squared as equal to k over m. Okay, so now this equation is a very important equation. It's going to be labelled star, and this is the equation of simple harmonic motion, and it's one of the key equations of physics that pops up all over the place. So you might also see this equation written slightly differently as, so it's equivalent to x double dot plus omega squared x equals 0. Okay, so this dot notation denotes a derivative with respect to time, so 2 dots indicate 2 derivatives. So another thing that you can get using this dot notation is that the velocity could be written as x dot, and just as it's written here, the acceleration is written as x double dot using this Newton's dot notation. So now we have an equation for the motion of a mass on a spring, and we want to try and solve it. So let's try for a trial solution x equals a, so some constant a, times cosine of lambda t, where a and lambda are both undetermined constants for now. So if we try this as Rx, we find that x dot equals minus a lambda times sine of lambda t, and then we can find that x double dot by differentiating again equals minus a times lambda squared times cos of lambda t. Having differentiated the cos to get a minus sign and getting an extra factor of lambda out the front from here, and differentiating again to turn the sine back into a cos, and then getting another factor of lambda to get the lambda squared. Okay, so now if we substitute these back into our star equation for simple harmonic motion, we get, so sub back into star, and we'll get minus a times lambda squared cos lambda t plus omega squared times a cos lambda t equals 0. Okay, so now we can look at this and clearly see that this equation will be valid. It will give us 0 if, so this is true if we have lambda squared equal to omega squared. Okay, so this implies that lambda equals omega. Now actually this implies that lambda equals plus or minus omega, because when we square root this we get a plus or minus, but we have cos of anything, so cos of theta for example equals cos of minus theta, because cosine is an even function, and so it doesn't matter whether we take positive or minus, so we're just going to take positive for convenience. Okay, so we find that x equals a times the cosine of omega t. Okay, so this is a solution of the simple harmonic motion equation star, and if you work through this by yourself you can also see that x equals, so a different constant b sine omega t is also a solution that works. Okay, and because equation star is a linear second order differential equation, we know that the sum of two solutions is also a solution. So then for a general solution, we can write a general solution is x equals a cos omega t plus b sine omega t. Okay, and this is the general equation, the general solution of the simple harmonic equation, where omega, which we defined earlier as k over m, root k over m, is the angular frequency in radians per unit time and we can get from this angular frequency the frequency and the period. So the frequency is related by the following equation. So the frequency is given by f equals omega over 2 pi, and we can also get the time period using the following equation. So we know that time period is 1 over the frequency, which, inverting this equation, would give us 2 pi over omega. Okay, so another way of writing this general solution is using trigonometric identities to turn this cosine and sine into a single cosine. So another way of writing the general solution, so let's just label this as 1, is x equals a prime, so there'll be a different constant outside at the front, which we just indicate by a prime, times the cosine of omega t plus some new phase factor phi. So a prime and phi are both constants, just like a and b were, and in this case a prime is called the amplitude. So this is the amplitude, and phi is the phase. Sometimes also called the phase angle, because it's a little bit like an angle because you're putting it into a cosine. So the two undetermined constants a and b in the general solution, or a prime and phi, reflect a freedom in the problem. So we need some extra information to fix them. And one way to know these, to fix these freedoms, is to know two parameters at time t equals 0. So these are called initial conditions. So if we knew two conditions on x at time t equals 0, we could sub those in, and we could solve two separate equations for two variables, a prime and phi, or a and b, if we use the other general solution, and then we could find out what they are. Now, we're going to see one of the many use of complex numbers in physics, and when you first meet complex numbers or imaginary numbers in maths, you might think that they're quite abstract and maybe like an interesting oddity, but they're not really useful for any real-world applications. But that actually couldn't be further from the truth. They're ubiquitous in physics and have innumerable applications, and this is just one of them. So using Euler's formula, so we can write Euler's formula, which is e to the I theta equals cos of theta plus I sine theta. We can write the general solution of the simple harmonic motion equation in this following form. So let's label this as 1 prime. So this can be written as x equals the real part of a prime e to the I omega t plus phi. Okay, so we're using the real part, which just gives us the part of this term which is only real, so we're getting rid of this I term just because we want to only be left with the cosine like we had here. And you can see that this phase theta, this angle theta, is now an omega t plus phi. So this can also be written as the real part of a prime e to the I phi times e to the I omega t, where all we've done here is separated out the exponentials, the omega t plus phi as an phi and an omega t term. And so now we can define a complex amplitude. So define a complex amplitude A by writing it as A equals A prime e to the I phi. So this in general is complex, it doesn't have to be real, and now we can write x equals the real part of A e to the I omega t. So the modulus of A, this complex amplitude that we defined, is the amplitude A prime of the oscillation, because using this definition, when we take the modulus of e to the I phi for any number phi will always be equal to 1, because we have a cosine theta plus I sine theta. So when we take the modulus of this, we'll get cos squared plus sine squared, which we know is always equal to 1, no matter what the angle theta is. So then we'll only be left with the modulus of A prime, and then that gives us just the amplitude, A prime. So, just writing this down, we have the modulus of A equals the original amplitude of oscillation, A prime, and we also get the phase, the argument of A is just the phase angle phi. So we often just ignore the RE that we write in front of this term in the general solution x, because we can actually also write just the complex quantity z equals A e to the I omega t without a real part in front. And in fact, this complex quantity itself is actually a solution of the following equation. So z double dot plus omega squared z equals 0, which is the same as the simple harmonic equation, simple harmonic motion equation that we had originally, but we've just replaced the x's with z's, which can be in general complex, whereas the x's are all real. So we can see this just by substituting this in. So we can differentiate z to get z dot, which equals I omega A e to the I omega t, which equals I omega times z. So z double dot will equal I omega squared times A e to the I omega t, which equals minus omega squared z. Okay, so summing this into this equation, we can see that clearly we have a minus omega squared z and an omega squared z, and that will equal 0 as we wanted. So now, why are complex numbers useful? We've got this, and we can see that this is an alternative way of writing the general solution using exponentials and complex numbers instead, but it might seem like we complicate things for no reason. Now, one thing that becomes a lot easier if you use complex numbers is looking at damped oscillations. So real oscillations don't last forever, as these above equations imply, but they're actually damped by friction, viscosity, air resistance, and other energy loss mechanisms. So consider a viscously damped mass on a spring. So just to draw something that could be happening, we can draw another rigid wall with a spring attached to it, with a mass, let's not draw it so far away, mass m again, and this time this mass is submerged in some liquid. So we can think of that as a viscous liquid. As the mass on the spring moves back and forth, it will be the water will be pushing against it, slowing down its motion. So again, let's just label on some axes. So we'll say that this is x equals 0, and we'll take this direction to be positive in x, and again we'll take this direction as positive for acceleration, and we'll write down the spring constant k. Okay, so we assume, this is an assumption that we're making, that viscosity opposes the motion proportionally to the speed x dot. So this gives a force, so it's a viscous force, minus bx dot, where b is a constant which controls the strength of the damping. So you can think of that as the viscosity of the fluid that this mass is submerged in. And of course, the more viscous the fluid, so think of a really thick liquid like honey or treacle, then this constant b would be much bigger than a less viscous fluid. So the negative sign is because it always acts against the motion. And now if we apply Newton's second law again, so apply N2, we get that mx double dot equals, so just writing a as x double dot in the very first line, equals minus kx, so that's the spring restoring force from the spring as we had from before, minus, so new force from the viscosity, minus bx dot. So just rewriting this all on one side, we have that mx double dot plus bx dot plus kx equals 0. Now dividing through by m and setting omega squared equals to k over m before, and now also defining gamma to be equal to b over m, we get the equation of damped simple harmonic motion. So the damped simple harmonic motion equation, damped to SHM, is given by x double dot plus gamma x dot plus omega squared x equals 0. So with this equation, if you tried the same trial solutions as before, you'd find that cos and sine are not solutions to this, but instead, motivated by the exponentials that we saw above, the complex exponentials, let's first swap for x and z because we're going to anticipate complex solutions. So we can just rewrite this as z double dot plus gamma z dot plus omega squared z equals 0. And then we can try z equals a e to the pt for some constants a and p. Now we can find the derivative of this to try and sub it back in there and see what we get for a and p. So we get z dot equals p a e to the pt, which is just equal to pz. And differentiating again, we can get z double dot equals p squared z. Okay, so if we substitute this back into the equation for damped simple harmonic motion, we find that p squared plus gamma p, subbing it into here, plus omega squared, all times z equals 0. And then if we assume that z is not equal to 0, so for the non-trivial case where z is not equal to 0, we then obtain a quadratic equation for p. So this is a quadratic equation. We will get that p squared plus gamma p plus omega squared equals 0 for this whole equation to be equal to 0. And then we can find the roots of this using the quadratic formula. So p equals minus gamma over 2 plus or minus the square root of gamma over 2 all squared minus omega squared. Okay, and then, so this is the general solution for P, which has 3 different regimes of damping. So there are different physical consequences which arise according to the sign of this discriminant here, gamma over 2 squared minus omega squared. If we have gamma less than 2 omega, So if this whole term is negative, then we have light or under damping. If we have gamma greater than 2 omega, so this term is positive, we'll get heavy or over damping. And if we have gamma equal to 2 omega, we'll get critical damping. So if we have gamma less than 2 omega, let's look at this case first. It's better to write this equation as P equals minus gamma over 2 plus or minus I times, then we take the negative of what's inside here, so omega squared minus gamma over 2 squared, all square rooted. Okay, now if we write defining omega prime as equal to omega squared minus gamma over 2 squared, square rooted, so just this term over here, and then also remembering the trial solution a e to the pt, then the solution is the real part, so we're just going to omit the real part, assuming we know to do that. Z equals a e to the minus gamma over 2 plus or minus I omega prime times t. And we can factor this into two terms, so a times e to the minus gamma t over 2 times e to the plus or minus I omega prime of t. And finally writing a being equal to the modulus of a times e to the I phi, and then also taking the real part, we find that x equals modulus of a e to the minus gamma t over 2 times the cos of omega prime t plus phi. Okay, so this is the general solution in the case of light damping. Now this is the first payoff of using complex exponentials instead of causes and sines from the offset. It's a lot easier to deal with a e to the pt in the original substitution than it is to deal with this expression. It's a lot more complicated to deal with this. And we can see that compared to the case without damping, we have that damping has reduced the oscillation frequency from omega to omega prime. We know that omega prime is smaller than omega. And it also adds an exponential decay term, e to the minus gamma t over 2, which will slowly decrease the overall amplitude of this solution x. So if we draw this general solution as a graph of displacement x against the time of oscillation t, then this will be an exponentially decaying oscillating function, where these oscillations will be, even though I haven't drawn it to look like it, the time period will stay the same, but the amplitude of the oscillations will decrease exponentially over time. Now let's look at the next case of heavy damping. So if we have gamma greater than 2 omega, then the system is said to be overdamped or heavily damped. And then the general solution we can find is the sum of two exponentials. So x equals a e to the p1t plus b e to the p2 times t, where if you went through the maths and found out, and I'd advise checking this just to make sure it does work, p1 equals minus gamma over 2 minus the square root of gamma over 2 squared minus omega squared. And p2 will be a similar term but with a plus sign here instead. So we get minus gamma over 2 plus the square root of gamma over 2 squared minus omega squared again. Okay, so both of these are negative, so these are both decaying exponentials with real terms in the exponential. So this is heavily damped simple harmonic motion with no oscillations occurring, and so if we drew a graph of this, of displacement against time, this would just look like exponential decay. Okay, and you can see there aren't any oscillations, so this is very different to the case above. Now, if we instead have critical damping, final case, where gamma equals to omega, there's only one solution for P. You have P equals minus gamma over 2. And this is actually of practical importance because critical damping ensures the most rapid return to zero. So even though here we have a return to zero, it's exponential decay, so it's decaying quite slowly. This takes a long time to decay. And this is used in things like car shock absorbers and other scientific instruments where you want oscillations to be minimized, and you want any oscillations to be damped and quickly return to zero. So mathematically, if we take the heavy damping case and set P1 equal to P2, which equals minus gamma over 2, we would end up with x equals a plus b times e to the minus gamma t over 2, and then just combining this a and b into one single constant, we can write that as a prime e to the minus gamma t over 2. And here, now that we only have one constant left, a prime, which isn't determined from the setup, so gamma is determined from the viscosity and the mass, we only have one degree of freedom, and we seem to have lost a degree of freedom. So with this solution, we could never have x equals 0 at t equals 0 without x equals 0 for all t, which makes no physical sense. So it actually turns out that t e to the minus gamma t over 2 is also a solution, and you can go and check that by substituting it back into the equation for damped simple harmonic motion. And so the general equation for the solution is actually a plus b times t, so we've just changed this a prime into an a again, without any loss of generality because they're just constants. A plus bt times e to the minus gamma t over 2. So once again, a and b here are fixed by the initial conditions. So if you draw a graph of this, the displacement against time, again for critical damping this time, it will actually look quite similar to the heavy damping graph, but the time scale that the damping is happening on and the time scale on which the oscillator returns back to equilibrium is a lot quicker than heavy damping case, so it'll actually look quite similar. Looks something like this. Okay, cool. So that was just an intro to simple harmonic motion, and simple harmonic motion appears all over the place in physics, and you can use these types of ideas and equations that we used to solve all sorts of problems. So just in chemistry, for example, if you take two particles that are close to each other in a lattice, you can approximate the bond between those two particles given certain conditions as actually a spring, and you can use simple harmonic motion equations to describe those as springs and then do these same sorts of calculations to actually get quite deep and profound results. In something I'm doing currently in quantum field theory, you also use simple harmonic oscillators all the time, and you approximate things as simple harmonic oscillators and springs, and you can use these equations again and again. And that's just two very small, that's just two specific examples when there are loads and loads of different examples where you can use this. So it is really interesting and good to get a hold of this, and good to get familiar with simple harmonic oscillators because they will appear all over the place. And it's also really interesting to see how complex numbers do enter in physics in very real world applications, and how you can use them to make your life a lot easier when solving equations, compared to if you just stuck with real numbers and use sines and cosines instead of complex exponentials instead. Thank you for listening, and I hope you enjoyed.